organizers for giving me the opportunity to visit the Isaac Newton Institute and to attend this workshop. So this is joint work with Emilian. All right, so let me start with some motivation. So I stole this part of it from Vernon's talk yesterday. So repeating Vernon, so in the perspective of climate change, we expect to see more frequent and powerful storms, therefore larger waves with potentially important consequences on the sea ice. So this is supported by field observations, and in particular, Kohu and collaborators observed a slow decay by large waves, possibly owing to nonlinear processes, which allows them to maintain ice breaking over large distances into the pack ice. So theoretically, to describe wave attenuation in sea ice, so much work has been done using separate flow models or viscoelastic type models. These are the two paradigms that Vernon referred to in his talk. And so here, in reference to that previous statement, we would like to propose and play with a phase resolved model for nonlinear wave propagation in fragmented sea ice. So it's a model that that is inspired by these two types that I just mentioned. So it combines the continuous and piecewise features, and can be used for direct numerical simulations in the time domain. But as you're going to see later, is ad hoc in a sense that you can see it as a mix of phase resolved simulation plus parametrizations. All right, and the goal is to try to emulate wave attenuation by scattering and possibly dissipation as observed in the marginal ISO. There has been some work done in this direction as well, with each different model method with its own pros and cons. And that's also true here. But I would say a nice feature of the model that I'm going to describe is that it's very efficient numerically. All right, so basic formulation. So I'm going to restrict myself to the 2D case, but this can be extended to 3D. In fact, that's what Olga discussed in the previous talk. So it's a bit embarrassing for me to talk about the 2D problem right after someone talked about the 3D problem. But anyway, so the same equations. So very quickly, the full equations for potential flow. For potential flow, and the ice sheet can be described by an additional pressure term in the Bernoulli condition at the top surface. So which is highlighted in red here. So this is, so I'm going to repeat a couple of things that Emilian and Olga already mentioned. So it's typically the situation of the thin plate of a thin elastic plate. So no inertia, no stretching, only bending. And for the time being, I'm only considering a continuous ice sheet, so no ice flows yet. So there's a number of models in the literature for P. Again, very briefly, Euler, the linear Euler-Bernoulli model, where P is a fourth derivative in eta. The nonlinear Kirchhoff model. But here, following Olga and Emilian, I'm going to use the nonlinear model by Plotnikov and Tolan, which is given by this expression. So again, in red, that's the mean curvature at any point on the top surface. And as a quick check, if you ignore the nonlinear term, so if you ignore the cubic term, if you ignore the eta x squared in the denominator, then you have the fourth derivative, and this reduces to that. All right, so again, Emilian already mentioned that, but let me say it one more time. So, so one thing that I particularly like about this model, about this formulation, is that it's both nonlinear and conservative, in the sense that you have this conserved energy in time. And therefore, so this would be the kinetic part of the energy, and this would be the potential part of the energy due to gravity and elasticity. And so therefore, this suggests the Hamiltonian formulation for nonlinear ice-covered ocean waves a la Zakharov. Indeed, if you just ignore the contribution in red, then this is the standard energy for water waves in the Zakharov formulation. So therefore, given the large amount of work that has been done using the Zakharov formulation, you can imagine that maybe similar things can be done for this problem with this formulation. In particular, you can do some analysis, you can do some simulation. So let me say more about this. All right, so in particular, let me say more about the Hamiltonian formulation. Again, I'm going to repeat a few things and how to solve this numerically. So we're solving a Laplace problem, so not surprisingly, the conjugate variables here are boundary variables. So eta, the ice sheet deformation, and the trace of the velocity potential at that location. And so in terms of these two, the boundary conditions at the top surface, so the kinematic and dynamic boundary conditions, can be expressed as a canonical Hamiltonian system, and this is what is written here. And the corresponding Hamiltonian is nothing but the energy the conserved energy that I just mentioned. And here it is explicitly written in terms of eta, one of the two conjugate variables, and you can do that thanks to this operator, so the Dirichlet-Neumann operator, so DNO. And according to the definition, you can see that it returns the normal fluid velocity at the top surface given eta xc, right? So indeed, this is a gradient, and this is the normal to the top surface, and you take the dot product, that's the normal velocity. All right, so more specifically, this is what the Hamiltonian equations look like. And as I said, it's a closed system for the two conjugate variables eta and c. And so this says that at a given time, if you know eta, if you know c, then you can evaluate their time derivatives according to the right-hand side and use that to update the solution. But to do that, you need to evaluate the DNO. Okay, so you need to find a way to determine the DNO. So Olga, Emilian, they have their own ways. So here I'm going to use this. In particular, I'm going to use the fact that the DNO is analytic with respect to eta, the top surface, under some regularity conditions on eta. In fact, this is a theorem, and therefore the DNO can be expressed in terms of a convergent Taylor series expansion in eta. So something like that, an infinite series. And one nice thing is that each Taylor term can be determined recursively, and this is what the recursion formula looks like. So it look so indeed. So you have two of them depending on whether j is even or odd. Indeed, this is a recursion formula because a g at one given order can be expressed in terms of g's at previous orders. So this is what I mean by recursion formula. And so it looks horrible, but do you agree it's very explicit? And in fact, you can easily code this on a computer. For example, by using MATLAB, it just takes a few lines by using, for example, some for loops. So it looks complicated, but in fact, it's very explicit. Oh, so this is the way we're going here, and so let me say a bit more about this expansion. So if you write down the first few terms, so G0, G1, G2. So because this is a Taylor series expansions, each G depends on powers of eta. So G2 would depend on eta squared. So you have some homogeneous dependence on eta. G1 would depend on eta to the power 1, and G0 would not have any dependence on eta. And so usually the more terms you take in the expansion, the better, meaning the more nonlinear your calculation is. And so another thing that I like about this formulation is that you can easily see the physics that is involved. So for those who are familiar with perturbation calculations for water waves, so you can see here that G0 corresponds to the linear approximation. G1, because you get C and C on both sides in the Hamiltonian, this corresponds to 3-wave interactions. And G2, again, because you have C and C on both sides, and you have an eta squared, this corresponds to 4-wave interaction and so on. All right. So you kind of like you're able to identify the physics that is involved. And as I said, the more terms you take in the expansion, the better usually. All right. So in my notation, D is minus I partial x. So I being the imaginary unit. So it's a Fourier multiplier. It's the same expansion whether you're in shallow water or deep water. And in the infinite depth limit, when h goes to infinity, then tanh tends to sine of d, and therefore G0 tends to absolute value of d. And that's the only change in the expansion. All right, so these are the equations that I would like to solve numerically. Okay, so how can you do that? So if I assume periodic boundary conditions in X, then a natural choice is to use a pseudospectral method. So in other words, you expand your two conjugate variables in Fourier series. And what is nice about this method is that you can easily evaluate derivatives and Fourier multipliers. For example, if you want to evaluate the first term in your DNO, G0 well, you take the Fourier transform of C, you multiply by K times HK, and then you take the inverse Fourier transform. In the same way for partial X of C, you multiply the Fourier coefficient by IK, you take the inverse Fourier transform, and you're done. And unlike local approximations, these are global computations. Therefore, they are very accurate and very efficient if you use the fast Fourier transform. We're not done yet. So in practice, the DNO series need to be truncated to a finite number of terms as well. But because you have this analyticity property, a small number of terms, typically less than 10, is sufficient to achieve accurate results. So for example, typically in our computation, we use M to be like 6 or 8. Usually that's enough. And for the purpose of the simulations, the equations are non-dimensionalized by using these quantities as unit length and unit speed, so that G is 1 in the equations, and sigma over rho is 1 as well. All right, so that was for the discretization in space. So pseudospectral method. Now, what about time integration? So we're solving the nonlinear equations. We're not in the time harmonic regime. So we're trying to solve the equations in the time domain. So you also need to integrate the equations in time. And again, here you can take advantage of the fact that you can move to the Fourier domain. So why is that an advantage? Because if you decompose your equations into something linear and something nonlinear, with a linear part that would contain G0C, the gravity term, the fourth derivative in the linear approximation. Note that so if you add in the linear part, then you need to subtract in the nonlinear part. If you add in the linear part for the elasticity term, you also need to so if you subtract here, then you need to add in the nonlinear part. So it is an advantage because so if you move to the Fourier domain, then you can integrate exactly the linear terms by the integrating factor technique. And in this case, the integrating factor here is given by this 2x2 matrix in terms of G0. In fact, in terms of the linear dispersion relation, which is not surprising because it is about the linear terms. So it's kind of obvious that it's going to involve the linear dispersion relation. But the nonlinear terms need to be solved numerically. You pick your favorite method. So what about fourth order Runge-Kutta? So the solution at time step n plus 1 in time is given by that in terms of the solutions at step n. And you can check that indeed the integration here, the numerical integration here, is just about the nonlinear terms. All right, so we have a good way of solving the equations numerically. In the case of a continuous ice sheet. Now back to my original problem. So how can you adapt or extend this approach, this formulation, to try to model fragmented sea ice, or more precisely a fragmented ice sheet? And you want to do that while preserving the nice features of the original formulation, of the original approach. And so we did something very simple. We just use smooth interpolation. So we add you can add a weighting factor to the pressure term, so that it is space dependent. So again, it's like just interpolation with F equals 0 for water and F equals 1 for ice, and in between you have a smooth but steep transition. And we also assume that the flow distribution is fixed in space and time, so therefore the weighting factor here is simply a function of space. And so the way we set up things is that we first specify a regular array of NF identical flows with length LF that are evenly distributed over some distance LC. And then afterwards, we slightly randomly move them. We randomly move by some small amount the center of gravity of each flow. And so at the bottom here, this is an example of a realization of such a flow distribution. So in this example here, for illustration, you have 5 flows with length 60 over a distance of 400. More precisely, between x equals 100 and x equals 500. So when f is 0, down here, this is water, and when f is 1, this is ice. And so if you count 1, 2, 3, 4, 5, you have 5 ice flows. And it looks discontinuous between the two phases at the edges, but if you zoom in, you're going to recognize the tangent profile, because that's typically what we use for the smooth transition between the two phases. All right, so you pick something smooth, so that kind of complies with the underlying formulation that is originally for a continuous ice sheet, but at the same time you pick something that is steep, so that you can easily distinguish the different flows. All right. So this is our model for our simple model for a fragmented ice sheet, and so we're going to perform simulations to quantify the attenuation of solitary waves as a function of a number of parameters. So the incident wave height, A, ice concentration, which is ice versus water area, and ice fragmentation, which is basically the number of ice floes. And so to quantify this attenuation, we're going to monitor the time evolution of two quantities, the instantaneous maximum elevation, and then the root mean square of eta. So so what is nice about okay, so so here we're looking at solitary waves. So you may ask why. So first nice thing about solitary waves is that in the absence of ice, so these two quantities are conserved in time. So therefore, you can use that as a reference. And in the presence of ice, these two are going to change over time, and that is going to be your measure of attenuation. Because again, we're solving things in the time domain. All right. So we need something as reference when there's no ice, and something that is going to change over time if you add ice. But in fact, I'm just going to show you results for the root mean square. Okay, so all right, so let me say it one more time because maybe it's not that. So here we're looking at solitary waves on shallow water, which is kind of an unusual situation. Again, if you have the ocean in mind. But as a preliminary study, that's what we picked for a number of reasons. One of them is what I just said on the previous slide. You can add more reasons if you like. One more reason, a solitary wave is the ultimate long wave. So therefore, this may help justify the use of a thin plate model. Over time, they remain somewhat localized, and therefore you don't need to worry about undesirable wave reflection or transmission from the lateral boundaries of the computational domain. Otherwise, you have to somehow take care of the boundary conditions. There are a good approximation to long swirl waves, which are particularly energetic and can travel far into the ice field. And this is an interesting situation because back to my motivation on the first slide by climate change and so on. And there's also a good approximation to tsunami, for which there have been interesting cases of interaction with floating ice. And one example is this one. So the March 2011 Tohoku tsunami. So not only hit Japan, but it also went across the Pacific Ocean and caused large Manhattan-sized icebergs like these two, again the size of Manhattan in New York City, to break off the ice shelf in Antarctica. So the effects could be impressive. A slide that I picked from Emilian's. So a tsunami induced by a landslide in an ice-covered lake near Montreal. So that would be another example. All right, so now what about the numerical results? So that's the first simulation. That's the first simulation for a highly fragmented case. So on the left, that's the initial condition. So a solitary wave of height 0.3 compared to depth equals 1. On the right side, that's the ice field. In blue, that's water. In red, that's the ice floes. And so the solution moved from left to right. Again, keep in mind when you look at plots, make sure you're aware of the units. So it looks kind of very steep, but in fact, if this is like over 400, and the vertical axis on up to 0.3. So in this case, over time, you see some reflection, you see some scattering with a slight decrease in amplitude, but otherwise, overall, the solitary wave is not much affected. So you kind of preserve the original shape. But now, if you slightly increase the size of the flows, like here, so the level of ice fragmentation is the same, but the ice concentration is slightly higher. Then you see that you have more attenuation. And note that the size of the flows is very comparable to the width of my solitary wave. So very likely here scattering is very important. That's the main mechanism behind this strong attenuation.
So in both cases, the width of the input is
the same. Sorry,
is
the same initial condition. Yes, the same initial condition, the same times. Now the other way around, if you have fewer flows, only 5, but they are much longer, then it seems that dispersion, or it seems like the dispersion of the spreading of the solitary wave plays an important role. So you still see some reflection, scattering, you still see some kind of loss of coherency, but the attenuation is less than the previous situation, right? If you compare the final times, right? It's less. So it gets messy, but the attenuation is less. And if you increase the size of the flow even further, then it's even more dispersion. All right. So this is what you see with these many oscillations behind the solution. And in fact, the dispersion is very much related to the presence of ice, right? As you can imagine. So this is another simulation with the same initial condition, but now you have a long flow, continuous, between 100 and 500, with the same initial conditions. And so dispersion here really is related to the presence of ice, and you can clearly see that this is especially strong when you have this, it is especially strong in this limiting case of a long continuous flow. And so what you see is that some radiation is emitted forward ahead of the main pulse. And so you may wonder why. So you can explain this, in fact, in the framework of the fifth order KdV equation. So you can derive a fourth order KdV equation in the situation for a continuous ice sheet. And so this kind of equation admits so-called generalized solitary wave solutions, meaning you have a pulse plus some dispersed tails. So this is a comparison between the food equations in solid line and the solution to the KdV equation in dashed line. So you see a central pulse plus some dispersive tails. So the wavelength of the dispersive tails can be estimated like that by using some kind of resonance conditions. But you also see that at least in the simulations, the dispersive tail only appears on one side of the solitary wave. And this can be determined by the value of its group velocity CG relative to that of its phase velocity. And so if CG is less than CP, then the ripples, the dispersive tails, appears behind the main pulse, otherwise they appear ahead of it. And in this hydroelastic problem, CG is less than CP if the wave number associated with the dispersive tail is less than K min, when you have the minimum of the dispersion relation, and larger otherwise. So if you put all the information together, in this particular case that I showed you earlier, this one here, C is 1137, H is 1. So therefore, you can find by just solving this equation that KD, the wave number for the dispersive tail, is 0.8. This is larger than K min, where you have the minimum of the dispersion relation. And therefore, accordingly, the ripples are ahead of the mean pulse, and that's exactly what you saw on the previous slide. All right, so now back to the attenuation. So these graphs show you the time evolution of the root mean square for various amplitudes A, from very small to larger. So 0.01, 0.02, 0.05, 0.1, 0.2, 0.3. This is for the most attenuating case, when the size of the flows is comparable, very comparable to the width of the solitary wave. And this is in blue. And as a reference for comparison, in red, that's the attenuation for a single long flow. Okay? So so you know that the attenuation for the single long flow has to do with dispersion, spreading. And so if you compare these two, blue and red, so a couple of observations. So the attenuation increases with the amplitude, right? You don't see much when the amplitude is small. You see more when the amplitude is larger. So increasing with the amplitude. For solitary waves, higher amplitude means shorter waves. So you have higher attenuations for shorter waves. So therefore, this is just a confirmation that scattering seems to be important in this problem. It seems to be the main contributor to attenuation because it's much lower than the red curve. This is for the opposite situation when you have fewer flows, but they are much longer, right? So in this case, it's more about dispersion, spreading. And indeed, well, you see some similar features, but because it's more about dispersion and spreading, the two curves, red and blue, they're closer together. And in fact, you see over time, and even for larger amplitudes, that blue is not below red anymore, right? So it's the other way around. So scattering doesn't play much here. It's more about spreading and dispersion. And because the red is the top one for dispersion, it's lower than blue. So if you put the graph together, so if you put the curves together on the same graph for the 4 different configurations, that's what you have. So as I said, where you have the strongest attenuations is when you have this nice combination of flow size and ice fragmentation and ice concentrations, and that's in red, lower than the other guys. The least attenuation is when it's very fragmented, nothing much happens. In that case, it's like this. By the way, the continuous line, these are the exponential fit. And you can see that for the least attenuating case, even a linear straight line would be okay. However, overall, you agree that, and that's especially true when the attenuation is strong, the exponential fit is not that good. And so what we found is that, at least, in that situations, a double exponential is a better fit. And you see why, right? So it's a better fit because you see that over time, the curve don't decay to 0, but they decay to a non-zero limit. Okay. Otherwise you will need something that decays to 0. So here it doesn't decay to 0, so that's why the exponential fit is not that great. Okay. And the reason, the physical reason why it doesn't decay to 0, because we're playing with solitary waves. And solitary waves, they're very stable. They're very stable. They're very persistent. So that's why they don't tend to 0 that easily. But still, so the fit are not that great, but you can still extract some attenuation rate to compare the different cases. So this is just another way to compare the situations by using the attenuation rate that you can extract from the fit. And again, it's just another way to look at things. Again, in red is always the most attenuating situations as a function of amplitude, as a function of ice concentrations. So this case here would correspond to the long continuous flow, and that situation is in black on the other side. I'm over time? Almost time. Great. So we can play with dissipations just to see what happens if you had dissipation in addition to the scattering. So you can add eddy viscosity. So this has been used in other situations. So the question is, why not here? And this is what we found. In blue, that's without viscosity. In red, that's with viscosity. And the main message is that when scattering is strong, when attenuation is strong, well, viscosity doesn't add much because the flows are very short. However, when ice concentration is high, then there's more difference. But again, this is just preliminary results. Well, anyway, so that's all. Thank you very much.
Thank you. Are there any questions?
Sorry about that.
Oh.
Just have one question. You know, at your numerical method, where you do this expansion, how does that compare to the high order spectral method that was used in the paper with, Felician, that you referenced? You know.
I think these two methods are similar.
Okay,
similar. Yeah.
Doing one quick one.
Yes.
Did you look at variation of water depth with your calculations in any way?
No. Yeah, I just fix H to be 1 as a reference, but then I change the amplitude, which in some ways is the same, right?
Okay.
So you fix one of them and you change the other one.
Change the other one.
Yeah. So that I can only play with a few parameters.
In your last statement, you say that you want quantitative validation against field observations.
Yes.
What type of field observations would you need?
Maybe some graph of attenuation rate as a function of wave period. It's not going to be with solitary waves. You need to change the incident wave conditions, but that would be a possibility, I would say. You can extract some attenuation rates from the curve and try to compare this as a function of, let's say, wave period.
What happened? Time series.
Okay, we must go for a photograph. Something that I would like to have asked, I'm not going to ask it, but I'll raise it, and that is the validity of the irrotationality of the flow assumption beneath the ice sheet.
Yeah.
Are there not currents and vorticity under there?
Yeah. Then you feed that into the gamma. It's a joke. It's a joke. This is one way to go.
Because it's no longer variation, it's no longer flow.
Pardon?
Okay,
Yeah.
let's go and have our photographs then.
Thank you.